So we're going to go through the proof that if t is a linear operator on V and p is the minimal polynomial, then there exists a vector alpha such that the t annihilator alpha is the minimal polynomial for t, and the invariant subspace, which is the cyclic group of alpha generated by the linear operator t, is t admissible. And remember, t admissible means that there exists a subgroup that is t invariant and a complement subgroup that is t invariant, such that the direct sum sums to V. So what we're going to do right now is we're going to prove the first step, and then in the next video we'll prove the second step. So in the first step, we start by supposing instead of p equaling a bunch of prime factors multiplied together, we suppose it equals one prime factor. And this pi is a prime factor, and as pi to the k equals 0, and pi applied to t to the k minus 1 doesn't equal 0, there exists a vector in our vector space such that pi t k minus 1 alpha doesn't equal 0. Because remember, as long as the operator doesn't equal 0 on our vector space, there exists a vector in our vector space that doesn't get mapped to 0. So now we use this idea and consider when the minimal polynomial is a multiple of many different prime factors, all to different powers. So for each of these for each of these values or prime factors, there exists an alpha I such that if we take the prime factor to the power 1 less alpha, this does not equal 0. But to the full power does equal 0. Which means that the t annihilator of that particular alpha I is the prime factor to the Ri. And that's what annihilates it. Now, remember that these alpha i's are t invariant to each of these subgroups, because by the primary decomposition theorem we can split this up into individual subgroups. And if we let alpha equal the sum of these alpha I values, and G be the annihilator of alpha, then by definition, G divides P. So if G is the t annihilator of alpha, well, it has to divide the minimal polynomial. But for each of these alpha i's, if we apply t to alpha I, we get 0, which means each of these prime factors up to the multiplicity, or the annihilator for each alpha I, divides G. And because G divides P and all the prime factors are in G, G and P are equal.